So in this video, I'm going to show you a simple reason behind all the mechanisms in my architecture. So the answer is more data, because more data makes AI smarter. So you can see here a trend in evolution is that more compute and more communications and storage and more data processing, that now they have recently made all of this. You can have the same compute in this size now. See that? So the compute and data, more data compute, and another thing is the algorithm itself. They're making the code faster and the algorithm's more efficient. So without having to get a better, faster computer, the algorithm can instead do the same thing. So I'm going to show you that why the mechanisms are using, collecting, and generating more data. And first I'm going to show you my working algorithm here. It doesn't have all the mechanisms, but it's simple and it will help you understand. So you can see on the internet the Hutter Prize compresses 100. The best algorithm can compress 100 megabytes to 14.8 megabytes, and that's the best compressor in the world. It's the best neural predictor of the next letter in a sentence. So my algorithm I copied someone else's and followed how exactly it works, and it came out to the same result. I made it from scratch, and it can compress 100 megabytes to 21.8 megabytes. And so I'm going to show you here how it basically works. So what happens is you have your text file of 100 megabytes, and I set it to 17 letter window as sliding one letter at a time along the whole file. And say you're at the middle now. For every offset it had went through, it stored it into the tree here, and so every 17 letters it's seen can be found in here, like walking, walker, way, ways, and every time it passes a node it increments the count. So the early layers will have higher frequency. Get it? So now say it's at some 17 letter window here. Before it saves it, it's predicting the next letter. So the way that works is you're going to look at the frequencies. You can look at what the frequency of the next letter probably is in the first layer, and then you can use the context of the 17 letters to find the 17 letters, 1, 2, 3, 4, 17, and then see what comes next after the context. And then you have the frequencies of the predictions. Maybe A comes next 5 times, B comes next 3 times, Z comes next 1 time only. And then, so when you look for a longer match, it's more precise, because the more context, the more data is better. So looking at the long window to predict the next letter, finding a match and seeing what comes next is better. Now, of course, when you get to the last layers, it's going to have very few counts, so not enough data. So what you want to do is you want to look for a short context, last 2 letters, see what comes next, predict the next letter. So you do, and see what comes next. You have a lot of counts, but the problem is the context is now short. You don't have a lot of data, even though it looks like you have a lot of data. So the way this works is that the best algorithms are context mixing the predictions from multiple variable lengths. So you're going to search for the last 17 letters, 16, 15, 14, all the way down to just a single letter that would come next. And then you're going to have all 17 matches. You're going to see what comes next after each of these. And so, like I said, you're going to take the last 17 letters, last 16, 15. You're going to find each of those in here. It sees what comes next. and you're going to mix those predictions. So you're going to start at the last deepest one you found, maybe 14 letters in the tree, and because the 17 letters might not ever been seen, so you only found 14, because you might not have 500 letters identically seen before in the file, so it's rare, not frequent. It's not really common to find that long of a match. So you're going to find that, say the longest you find is 14, and then you're going to see how many counts. You might have not enough counts, you might have enough counts. Maybe by 12 matches you have enough counts, then you stop. So you're going to mix together 14, 13, and 12 letter matches predictions, because you have enough counts, really, so you don't need to pay attention to the lower context. So you're going to mix those together more to get more weight. So that's how my algorithm works. It is mixing those together. And another thing my algorithm does is, so that's the basic idea. I can use the activation function with that, and what happens is energy in my algorithm, how many predictions, so you got 1, 2, 3, it will split the energy, and you need enough counts in total. Like if you have 3 of these and you have 20 counts total, that's not enough. But if you have one prediction with 20, then it's enough. So the energy gets split, and it decides how much weight that will get. Do you need to look at the shorter context? So that's basically how my algorithm works, mostly, is you're doing that. Now, I'm going to show you my true hierarchy here. My algorithm could be ran in this. It actually looked like this because you need every offset. So here's the hierarchy. You build features using smaller parts, and it can run this here. And so this would be able to run it. And what happens is that, so that's how my algorithm works. We'll stick to this for now for the demonstration here, so because it's more easier on the eyes to understand the hierarchy. So that's how my algorithm works. I can compress 100 megabytes to 21.8 megabytes or so, and so because I can actually make it even more compressed if I set the settings better, although that's just because I set it to hard code it a little bit on some of the numbers, so I didn't make it most optimal. So what happens now is, so you have the hierarchy. Now with my algorithm, you would increment frequencies, you'd update the weights every time you pass them. So you take every 17 letters of the window that you see in your life as you scan along the file, you take the 17, save it in here, 1, 2, 3, 4, 17, and you're incrementing each count you pass on the weight, the connection. So you have a hierarchy, you have the weights, and you're updating them, and so it's based on the data, so not the back propagation. So now you can already see here, now in my algorithm, you have to understand that I've tested it. Every time I add more data, like say I don't do the whole 100 megabytes, if I do 500 kilobytes or 600 kilobytes, the more data improves the compression. So it's like perplexity when you do the evaluation on the prediction neural network, the predictor. So if you add more data, I can see in my evaluation that the compression improves, and it always does that. Even if you add only 1 kilobyte of data, that the prediction is improving, the compression is smaller. So like you can have only 3 kilobytes, the compression is only like 3 kilobytes to like 1.5 kilobytes, so it's only like half the compression. If you do it on 100 megabytes, like I said, it's 21.8, that's 4 times the compression. So the more data, the better the prediction. So we can see here with my hierarchy, if you have the hierarchy and you got the weights and you're updating them, so more data is making the prediction better because it has more experience, can see what comes next. So if you add more data, it's a better prediction. Now, when you look at the last 17 letters of this toy algorithm I made, you're going to look for the 17 letters and then sees what letters comes next in the forward propagation to the right words of the node. So you found a match, say 1, 2, 3, 17, and you're seeing what the 18th letter is, and you get the prediction, what's on the right side of the node or the parent node. So if you have a lot of counts on it, you can predict, well, 5 times it's seen P come next, 3 times it's seen B come next, 2 times it's seen Z come next. So you got a lot of data, you can predict well what probably comes next after those 17 letter match. Now, so more data is helping it. Now, if you are doing the variable mixing like my algorithm does, you're looking for the last 16 letter, 15 letter, 13 letter. So you're going to activate all 17 or up to 17 matches in the hierarchy. So you're going to activate this node, that node, that node. So, 17 letter, 16 letter, 15 letter matches. And you're going to take every one of those nodes and take the predictions of what comes after each of those. And they'll have shared parent nodes. So, dogs can jump and jump and jump and jump and jump will all point to similar parent node predictions. So, dogs will point to J or jump, and Ken will point to J and jump. And so, as you can see there, you get more data when you take multiple nodes and sees what comes next after them. So when you mix the predictions, you're getting more data, because when you think about it, like I told you, when you find a long match, but only a long match, it's more context, but you have seen it fewer times, so it's less data actually. When you look for a short context match, P say, see what comes next, it's small context data, but you have a lot of counts on it, you've seen lots, but it's not really that good then, so it's half this, half that. So if you go for all 17 and you mix them together, you give less weight to the 17. In the algorithm I made, you can divide the 17 matches by 17, so each one gets even weight, but it's better to look at if you have enough counts in the layer. So you might stop and not really mix in the 3-letter match in the hierarchy. But anyway, the way it works here is that you want to look at all 17 or up to 17 and mix the predictions, because if you have 17 of them, even though none of them are really perfect, you're getting 17 times the data basically, and that's better. So more data. So you're getting more data. Now, the next thing I want to show you here in my architecture is the translation. If you input a phrase like "the cat ran," it doesn't just activate the cat ran at he cat ran, cat ran, at ran, ran, and it also activates that cat ran, that dog ran, this dog jumped. So it activates all sorts of related word nodes. And so if you take all these nodes, because you're going to take, so remember how I told you with the exact match, you get 17, up to 17 activation matches, right? Well, if you're doing the dog ran, the zebra ran, this zebra ran, you're going to get 17 times 50. So you're going to get a lot of activations in the network. So then you're going to mix all those together. It sees what comes next after each one of those nodes. And you're going to mix all the predictions, get one final set of predicted letters. So you're going to get 256 predicted bytes, letters. They're 1 byte long, of course, if it's one letter. So you're going to get one set of predictions after you mix them all together. So in doing so, you get more data because you got more nodes activated because they share the same parent. So, because if you got cats and dogs usually have the same word come next after them. So they're very related. So obviously if you got cats go in, you can take dogs, it will activate it through shared pathways, and then dogs will have, because we already activated it because it had shared parents, a lot of them, triggers that relate through local paths, the related node. And because of that, it is also going to activate its predictions, and they will probably be correct or even shared by other nodes. Sheep and zebra and dogs will all see it come next 8. Dogs 8, zebras 8. So that's very helpful. You get more data. So see, it's all about data. Now, remember I told you with my algorithm, if I add more data to it, it's a better prediction. Well, with the 100 megabytes and Wiki 8 data set, you can't add more data because it's a prize, it's a test to see what you can do with 100 megabytes and no more. So with 100 megabytes, you get a compression, but you need to make a better algorithm that's smarter to find patterns. So it's got to find patterns in the same data set size without adding data. So the way to improve the prediction, the compression, the evaluation of the predictor network is, if you're not adding more data and you need to use 100 megabytes only, the way to improve the prediction is to add more data. And you do that by generating virtual free data, like I showed you here. You're going to take the 17 matches, you're going to take 17 matches of all possible related word matches, like I told you. And then so you're getting more data for free, because obviously cats and dogs, you have free interchangeable words in the data set based on the shared context around them. So now another thing is, when activations happen in the network, energy remains in the node for a while. It doesn't fade away. So when you read on the paper, the cat's seen some cats running, and the cat I bought seen a cat go near a, and so all these words are off of the paper now and in your brain. They're being held in your brain, and you can even see that at night when you're dreaming, that the last day is all held in your memory and triggering your dreams to be like the last day of experiences, and even your thoughts too. And so what happens is that activations are held in your brain, and so if you've seen cat come the last 5 times, it's going to be pretty activated. Now, recent words heard will be more prominent in the node cats. So recent activations have more energy before fading off and leaking. So what happens is that if you've seen cat, and you have a very small data set, it will actually help to have a pre-activated temporary forgetting, so it will help because the next word probably is cat if you've seen it 100 times. So instead of using a data set, like you have a big data set, you can use actually a small data set. You can get a lot of data just knowing that if it's already activated, it's probably going to be activated again. So that in a sense gives you free data because it's already activated. So because when your nodes are activated in the brain, they're activated for a while to hold the sentence you read, and so obviously that's going to affect the predictions, because if you're predicting the next word might be cat, and obviously cat is being held in your brain, it's already pre-activated. So that basically adds more data to your data set, because even though you're not increasing your data set, you still get data, because like I said, it's, if you've seen that, Now, the other way it works too is that because with related words they're the same, if you've seen a sentence with like, dog, cat, horse, dog, the farm, that's going to trigger predictions that are all related to those words. So cat will trigger horse, zebra, farm. Farm in your sentence will trigger farm, barn, sheep, zebra, horse. So all these related words are upvoting related words to predict. So when you read a sentence, all these words are activated in your brain and they're all leaking energy to related words, and then they all have predictions. Well, they are the predictions. They are causing the related. They're causing to. They are boosting the predictions. So this temporary energy, you can forget the password is car, but you'll store the node, and that's temporary energy. And the brain is also pruning weak nodes that haven't been seen a lot, and that actually helps the brain. Your storage, you don't need to store a lot. So, and that helps the prediction. Well, I guess actually it doesn't, because it makes it a little bit less precise. But that's very helpful. And so pruning is permanent forgetting, and then the temporary energy you just forget about. So it's adaptive, really. And so you're based on the local context, what is currently going to come next. If you're all in the zone of cats, cat, 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 and you're in a pattern, you're going to predict cat. Now, so we went through the translation, the energy, and then the reward. Reward is permanent energy. You have installed from birth, at birth, the certain reward on the node, like food and survival, shelter. So you can't really change that off the node ever, but it will leak to related words like food to money through shared pathway context, because like dogs and cats, dogs eat, cats eat, so they leak through this shared path. So with food and money, food, money, job, pleasing customers, so the reward is leaking, and those are more changeable. You can change the goal of a game. So what happens here is that can help predict the next words, because they're usually based about the root goal, survival. So basically, like I said here, you're getting a lot of free data for free. It's a virtual free data you're extracting from the same data set. And so as I've shown you here, all the mechanisms, well, this isn't all the mechanisms, but it's most of them. Get the basic idea. The mechanisms in my architecture are based on data. More data from more similar sources, it's helping it predict better, because you got more data. Because more data, you're going to predict better. You need a lot of data experience to predict better from lots of different situations. So because the data, if you take text, it can explain a lot of things. It's very flexible, and there's a lot of it on the internet, and it can go really far. And where video, you might not usually see a picture of Mars or a video of an apple being cut in 8 pieces, thrown at a wall. So text, you can easily find it on the internet. It can go into a lot of fantasies, the text. So it's very more flexible and more efficient. It's actually powerful, and it mirrors the real world too. So it's kind of like real data, and it's powerful, flexible. So basically, yeah, so more data is helping it predict better. So, and then the reward, so you got the maze, you understand the model of the world, lots of things about the world, different situations or contexts. Like a reinforcement learning in a robot is very limited. The brain can think about a lot of different scenery and situations. And so what happens is that you have the maze here, understands the world of what can come next, the truth, the prediction, modeling it all. And then the reward is trying to bring it to a desired outcome. And then so anyway, you have here the more data makes it smarter, and it is getting more data through all these mechanisms without actually increasing the data set size. So it is definitely a trend, and I explained to you how those mechanisms in here work. And the prediction is all based on the data, so you don't really need to do back propagation. We really need to understand how it's working. So that's pretty much all I wanted to show you.